morning. Okay, so welcome to Math 140 Calc 2. So what I want to do in this lecture today is talk a little bit about some basic results from algebra and trigonometry that we will be using throughout the semester. And I want to do them in such a way that we actually talk about some of the most important mathematics that there is. It's the mathematics of circles. So much of what we do comes down to circles and the formulas for the circles. I want to give you a sense of where they come from, why they're true, and why we use the units we do. So before class today, a couple of us were talking about natural logs versus logs and other bases, and why do we use base e, why don't we use base 10 or other bases? Well, when you're looking at circles, the Babylonians did things with 360 degrees. And the reason they chose 360 and 60, they worked base 60, is that 60 splits beautifully into a lot of different integer multiples. So 60 is divisible by 1, by 2, by 3, by 4, by 5, by 6, not by 7, not by 8, but a lot of other ones, 10, 12, 15. So you can split things up evenly. But when we do calculus, we do things with 2 pi radians rather than 360 degrees. So where does all this come from? And so we're going to talk a little bit about that. And the motivation is to try to get a formula for pi. And in doing so, we're going to encounter limiting processes. And this is one of the big ideas in calculus. And Archimedes, who's responsible for a lot of these formulas, was so close to calculus thousands of years ago. So it's what happens in the limit. What happens if we keep doing things again and again and again and again? Does it converge to something? And if so, what does it converge to? So again, there's many wonderful formulas for pi. I'm going to assume for now that you know that the area of a circle of radius r is pi r squared, and the perimeter is 2 pi r. It's actually not too bad to see that the area has to grow proportionally with the radius squared. It's going to be an area. If I double the radius, it should be 4 times as big. The perimeter is more linear. These are very reasonable formulas to have, and we'll see that they're true. What's amazing is that you can compute these constants, pi and 2 pi. There's a lot more information in the slides than I'm going to cover today. I'm trying to review a tremendous amount of material in a limited amount of time. I view myself as, Dorothy from The Wizard of Oz. If you remember the scene when she's captured by the Wicked Witch and you have the hourglass that's running out, and as soon as it's out, she's dead. This is how I view all the material that we need to cover. So if there are things that I'm talking about that you want to hear, by all means, ask me to slow down and say, hey, can you talk about this further? But I'm also putting in additional information on the slides for you to look at later if you're interested, or just talk to me in the TAs. All right, so the first formula, and we'll actually prove this later in the semester when we start doing integration, is the Gregory-Leibniz formula for pi. But it's actually a formula for pi over 4, and it's the alternating sum of the reciprocals of the odds, 1 minus a third plus a fifth minus a seventh. So when you have formulas like this, the first question is, does a sum like this converge? And when you take Calc 3, we actually do stuff about sequences and series and when stuff like this converges. This one isn't too bad to show it converges, because you can notice that because 1/3 is greater than 1/5, when you go down by a third and then up by a fifth, you're never going to go back below where you were. You're going to undershoot at minus a third. And then when you go up to 1/5, you're going to overshoot. So it's going to be getting closer and closer and closer to the true value. But unfortunately, it takes a long time for this series to settle down and give you the exact answer, or at least a close approximation. And that's a big theme in mathematics. A lot of problems become too hard to solve exactly, so we want to approximate the answer. So we'll prove this later in the semester, but let's see if we can make the algebra a little bit better right now. So if you have 1 minus a third, 1/5 minus 1/7, 1/9 minus 1/11, if you just look at it and you actually perform the algebra, you get 2/3, 2/35, 2/99. Does anybody notice anything about the numbers 3, 35, and 99? So these numbers are all 1 less than a square. It's 4 minus 1, 36 minus 1, 100 minus 1. And if you look at 4 is 2 squared. That's the number between the denominators 1 and 3. 36 is 6 squared. That's the denominator between 5 and 7, and so on. And so when we write it like that, we make the formula a lot easier to use. Now we're only going to have positive terms in our sum, and we're only going to have half as many terms to sum. So this is going to be much better in terms of accuracy and convergence. And so we can write the formula a bit more concisely as it is on the bottom. And so we get, the following formula for pi when we just multiply through by 4. Well, let's see how quickly it converges. So let's take some values. The first few lines is just some code I wrote in Mathematica to just actually do these calculations and just, calculate the terms. I will give several opportunities to learn coding throughout the semester. If anybody's interested, always happy to chat. So when n equals 1, the approximation we get is 8/3 or 2.6. Okay, not so great. When n equals 11, we get a nice rational approximation, very large denominators and numerators. It's about 3.09. So we haven't even gotten to 3.1 yet. At 21, we do have 3.11779. At 31, it's 3.125. So at 31 terms, and remember, this is really the same as 62 because we've combined things, we still don't even have 3.14. So if we go all the way up to 1,000 terms, which is really 2,000, we get 3.14109. All right, so we finally got 3 decimal digits. If we take 1,000,000 terms, it's 3.1415921. Getting close, but you can see it's very, very slowly converging. We don't even have the 2.6 yet. And a lot of people know pi to 3.1415926. We haven't even reached that with 1,000,000 terms. And these are very large denominators. When we're looking at 1 over 1,000,000 squared minus 1, you want to be able to evaluate that and add this accurately. This becomes a precision nightmare. All right, so let's find better ways to get this, and this is going to allow us to review some of the big functions in mathematics. So one of the gems is the Pythagorean theorem. So it says if you have a right triangle ABC, then a squared plus b squared equals c squared. So we will see later why this is such an important formula in mathematics. Why do we care? Well, here's one big application. Let's say you want to know how far apart something is. As a Bostonian, I hate New York City, but I have to admit that there is one thing that New York City does better than Boston. If anybody wants to try to say that, you are welcome to do so, but if you say a certain thing, you will fail this class. What must I tip my hat to for at least part of New York City over Boston?
I mean, I'm a Bostonian too, but I think New York City's roads are much better.
Yes, absolutely. If you had said baseball, you would have failed the class. So roads, the Manhattan grid system is very good, to describe exactly where you are and how to go. In Boston, you actually have roads crossing each other and flipping which one is above the other. We can use the Pythagorean formula to find out how far apart 2 points are. And so if we form a triangle, with those 2 points, so I want to know the distance between 2 red points. Here's the canonical example. It's 3 units to the east, it's 4 units north. So 3 squared plus 4 squared is 5 squared. So the distance is going to be 5. So this is one of the real most important applications of the Pythagorean formula, is that we can calculate these distances. A related question, which is of interest for mathematicians, is which integers can satisfy this? When can you find a, b, and c all integers that satisfy this? If you take 2 of a and b, you can always figure out what c is, but when can you get all 3 to be integers? There are a lot of proofs of Pythagoras. This proof goes back over 2,000 years. And like most geometry proofs of important results, you draw a lot of auxiliary lines. And part of the purpose of this class is to try to teach you how can you attack things? How can you try to figure out how you should prove things? A lot of times it's just trial and error. And then after a while, you start to gain some experience and some familiarity, and you have a better sense of what you should try to do. We're trying to do something with right angles. So every time I draw something that makes a right triangle, that's very good. So drawing the line from B all the way down to M, that's giving me a right angle. And then maybe I should connect B to E because that will give me a right triangle as well. So if you use logic like that, this might explain some of the choices being made. I still find this hard to follow. Here is basically the same proof, but now in color. I still find it difficult. Now, if you found these proofs bad, to me, this one is a monster. There must be some rhyme and reason behind why people chose to cut things up this way. Why do you think they colored things the way they did? So why do you think things are colored and labeled the way they are?
Do they have the same area?
Yeah, they probably have the same area. So there's got to be some way to show that the two 2s have the same area, the two 4s have the same area, the two 5s have the same area, and so on and so on. You're looking at it, to me, it's not at all clear. But maybe, if you start playing with, drawing lines and whatnot, you can prove, okay, maybe for the one, I'm going down by that diagonal, and then I'm moving over to the right by that, and then you start playing these games, and you might be able to see where this comes from. So if you want, as a good extra credit exercise, go through this proof and show that all of these polygons have the same area as the corresponding one. So I'm going to prove the Pythagorean formula for you. I'm sorry, yeah. And I'm going to start by clearly stating what are the assumptions. So I'm going to assume a couple of things. The first is I'm going to assume everybody knows what the area of a rectangle is. That's going to be one of our fundamental ideas. The area of a rectangle that's x by y is just x times y, base times height. And I sent you an article by Isaac Asimov about Euclid and the challenges of making assumptions. And you're trying to figure out what should be the assumptions that we use for geometry. Well, this seems a reasonable one. Area is just length times width. The next one is the area of a right triangle is 1/2 base times height. And so what we're really doing here is if we draw a diagonal, we have two similar triangles, and we are assuming that the area of a triangle doesn't change if you rotate it or if you translate it in the plane. And under that assumption, then since the two of them have the same area and they add up to xy, each one has to have area 1/2 xy. Okay, so this is the first proof of Pythagoras that I remember. And I saw this when I was a freshman at Yale in a physics class. And what you do is you take the triangle AB and you make 4 copies of it. And you go A to B and so on and so on. And then with a little bit of work, you can show that the quadrilateral, the rhombus inside with all sides of length C, that it has 4 right angles. So the area of the big triangle of the big square of side A plus B is just A plus B squared. And it has to be equal to the area of 4 of the right triangles plus the area of the square with C. And so you get A squared plus 2AB plus B squared is C squared plus 2AB. The 2AB's cancel, and you get A squared plus B squared equals C squared. Another way to prove this is to just regroup the triangles. And so I've got 2 different pictures. And if I put the triangles in different ways, I get A squared B squared and 4 triangles. And so these 2 must be the same. So C squared must be A squared plus B squared. So this is another beautiful geometric proof. Now, we are at Williams College. So you are not allowed, or you should not be allowed, to talk about the Pythagorean theorem without mentioning one of our most famous graduates, James Garfield, who is known in some circles as becoming president of the United States of America, but more importantly is actually credited with a proof of the Pythagorean theorem. You may argue that his proof looks suspiciously similar to things we were doing here, but as a Williams professor, I will not so argue. Anybody know where Garfield was killed or what he was doing when he was killed? So he was coming back to Williams for his 25th reunion, I believe. So, all right. So here are 5 possible Pythagorean theorems. We know they're all wrong. One of the things I want you to get out of this class is learning about how to think about math, how to think about objects that you're trying to model. And so for 4 of these 5, you can come up with a really good reason as to why it could not possibly be true. And so does anybody have any thoughts as to why any of these can't possibly be true? So when you look at these, do any of these look suspicious that there's no way that could be the Pythagorean theorem.
The second one.
Okay, good. What's wrong with the second one?
Well, I'm kind of biased because I know what the Pythagorean theorem is, but it's a constant on one side and it's not reflected on the other, I guess.
You're close. If we had 17a squared plus 17b squared, I would say that would be much better. It's the fact that it's asymmetric in A and B. To me, that seems suspicious. What about the third one? Does anything look suspicious about the third one?
I would be a little confused why, if I guess two have kind of the same relationship, why one would be, it's almost like the B value is decreasing the A value, which just kind of seems almost counterintuitive in a way.
Right, but so what would happen in the special case that A equals B?
I guess it would be 0, making the
You would
one
get
side
0.
0. So
And
it would
if
be like
B
no
is-
triangle.
Right, and if B is larger than A, you would get C squared as a negative number. So the third one has issues. For the first one, think about units. If A, B, and C are in meters, the left-hand side is in meters squared, but the right-hand side is in meters to the 17th. There are reasons why the fifth one is wrong, and I will skip that. And there are reasons to explain why the fourth one is a possibility. It actually passes every test you can think of. It's symmetric. C is going to be less than A plus B. But it turns out, of course, it is false. Okay, so let me give you a dimensional analysis proof of the Pythagorean theorem. This is one of my favorite proofs. And again, it's a good way to start looking at problems at a high level and see what's really coming into play. So let's think about area. Area is a function of the hypotenuse C and the angle x. And we'll see later with some trigonometry, when we review trigonometry, that A is going to just be C sine x and B is going to just be C cosine x. And so of course the area is going to be C squared times sine x cosine x over 2. But if you think about it, if I triple C, I'm going to triple A, I'm going to triple B, and since the area is 1/2 AB, the area goes up by a factor of 9. So the area should be proportional to C squared. And since it's proportional to C squared, I can write the area as a function of C and X as some function of the angle X times C squared. So I don't know what that function F is, but I know there's some kind of relationship like this. Now, most good geometry proofs, as I told you, at some point have us drawing an auxiliary line. So we need right angles. Can anybody think of a way to draw a line here and get a right angle? Where should I draw a line from and how should I draw it?
You could go to a vertical line from B to the top.
Good, so I could go from B just straight up to the top to C, and that would give me a right triangle, and that would give me similar triangles. So that's not going to work for this, but that will work for other things, for other constructions in geometry. So that's a great thing to try. It works for other problems, but not for this one. So how else, and of course you could do from A to C. So how else could I draw a right angle?
You could draw, I think, an altitude from the angle between A and B to C.
Yeah. And so I could draw an altitude from the right angle to C. And when I do that, I'm going to give the new triangles the very boring names of triangle 1 and triangle 2. And with a little bit of algebra, and you should try to make sure that you can do this, you can see that triangle 1 has an angle of x. And so all three triangles are similar. And so since all three triangles are similar, we can do a lot. What can we do? Well, we know that the area is just proportional to the hypotenuse squared. And the proportionality is just f of the angle x. So since they all have an angle x, and triangle 1 plus triangle 2 equals triangle 3, f of x times a squared plus f of x times b squared equals f of x times c squared. So what do I do now?
Can you divide everything by f of x?
I do, but I'm a math professor, so what do I have to do before I divide by f of x? So before I divide everything by f of x, what do I have to check? What's the one thing you have to be careful about when you divide?
Is it to make sure f of x does not equal 0?
I have to make sure f of x is not 0. If f of x is 0, I can't divide by 0. So you're absolutely right. I want to divide by f of x. And then I get a squared plus b squared equals c squared. Well, if f of x is 0, then the area is 0. So I know f of x is not 0, so all is good. All right, so now let's start to review a little bit of trigonometry. So if I give you a right triangle and I have an angle of a, then we're going to introduce new functions cosine and sine. So cosine of a is going to be the length of the base, and sine of a is going to be the length of the hypotenuse. Oh no, of the height. And so the other thing is we sometimes say cosine is the adjacent side, sine is the opposite side. And so this is a triangle with hypotenuse 1. If I give you a triangle with hypotenuse h, well, these are similar triangles, so I just rescale. So if I'm now 5 times as long as I was before, then the base and the height are 5 times as long as before. And so the base is now h times cosine of a, and the height is just h times sine of a. Now, of course, instead of looking at the angle on the bottom, A, I could look at the angle top, B. And if I use that, I then get it's going to be cosine of B and sine of B. And so we've immediately shown that when A plus B add up to 90 degrees, and most importantly, A and B are between 0 and 90, then cosine A equals sine of B, and sine of A equals cosine of B. So we have some beautiful relations between sine and cosine just from the definition, but we've only proven these relations initially when the angles add up to 90 and A and B are at most 90 degrees. Okay, so you should have seen plots of sine and cosine. And so the top is a plot of cosine, the bottom is a plot of sine. You can see they're essentially the same function, they're just shifted by 90 degrees. These are very different than the functions we've seen when we look at polynomials. The polynomials, they go off to infinity. These functions are bounded, they oscillate. And it turns out that there's a lot that you can do with these functions. So before doing too much with the trig functions, I want to talk a little bit about equations of lines. And the reason is, when we do calculus, one of the main themes in differential calculus, Calc 1, is that if I give you a really complicated function, locally it looks like a line. This is the tangent line concept. And we're going to do a lot more with the tangent line concept on Wednesday's class. And so I want to just quickly review what is an equation of a line. So a line is the form y equals mx plus b, m is the slope, and b is the intercept. That's where it hits the y-axis. So they often define slope as rise over run. So if I move over 1 unit in the x direction, how many units up do I go in the y? So for this one, we see here, if I move over 1 unit in x, moving 1 blue block, I move up 2 blue blocks for y. So the slope is 2, and it hits the y-axis at -3. So my m is 2, my b is -3. In a lot of the calculations we need to do, we need to multiply expressions. And so hopefully you've seen or heard the phrase FOIL before, first, outside, inside, last. So if I have a plus b times c plus d, it's ac plus ad plus bc plus bd. Now, because addition is commutative, that means the order doesn't matter. If you write things down in a different order, that's fine. You could do a times c plus b times c plus a times d plus b times d. That would be absolutely fine, as long as you get each term once and only once. So if I give you x plus y times x minus y, we see a lot of things cancel. It's just x squared minus y squared. In some of the calculations we're going to do, we'll encounter mx minus 1 squared. And so when you multiply this out slowly and just put in all the pieces, it simplifies to m squared x squared minus 2mx plus 1. Okay, so I'm going to just briefly talk a little bit about finding Pythagorean triples, and just, when, can we find triples of integers that satisfy this? So everybody should know 3, 4, 5. Does anybody know any other Pythagorean triples? There's often one other one that people know. So 5, 12, 13 is another one. This is a great example of a problem that's easy in one direction and hard in another. While it may be hard to find a Pythagorean triple, if I give you a candidate, it's very easy for you to check and see if it works. You just have to plug in and see, does a squared plus b squared equal c squared? So if I'm trying to find integers that satisfy this, I can divide both sides of the equation by c squared, and I'll get a over c squared plus b over c squared equals 1. So I'm now finding points with rational coordinates on the unit circle. And so if I can find all the points with rational coordinates on the unit circle, I can find all the Pythagorean triples. And it turns out that there's a couple of points that are easy to find. These are the points on the axes, 1, 0, 0, 1, and so on. And what you can do is you can draw a line. So imagine you have a point x, y with rational coordinates, and you draw a line from 0, -1 to that point. It turns out that that line is going to have an integer slope. So it's going to have a rational slope and a rational intercept. And so you get, y equals mx plus b, and x squared plus y squared equals 1. So you can substitute in for y mx plus b and expand everything out. And when you do a bunch of algebra at the end, and you write the slope m as p over q, you get 2pq squared plus p squared minus q squared squared equals p squared plus q squared squared at the bottom. And so we can use this to write down in explicit format all the Pythagorean triples. And now what you can do is you can take p, q, and just calculate 2pq, p squared minus q squared, p squared plus q squared. And so I've done a bunch of them. And if you want for extra credit, look at this table and come up with some conjectures on, maybe what are some of the possibilities for the integer triples? Do you think you have infinitely many triples of this form? Do you think you have no integer triples of this form? But the theme here is the importance of gathering data. So when we're trying to figure out what's true about these Pythagorean triples, we can write down an explicit formula for them, and we can generate a table of data. And once we have that table of data, we can try to figure out some interesting patterns. All right, so I want to quickly review some trig identities. So before class today, we were talking about what is the derivative of the natural log? Well, the natural log of x has derivative 1 over x. What's the derivative of the natural log of 5 times x? One way to do this is to use either the chain or the multiple rule and say the derivative of the natural log of 5x, it's 1 over 5x times the derivative of 5x, which is 5, and so you get 1 over x. And unfortunately, when people use the chain rule, very, very often they forget that if you have f of g of x, the derivative is f prime at g of x times g prime of x. They forget that g prime of x, they forget that factor of 5. Another way to take the derivative of the natural log of 5x is it's the same as the natural log of 5 plus the natural log of x. We're using the log of a product as the sum of the logs. Well, what's nice about this is we know the derivative of a constant is 0, so the derivative of the natural log of 5 plus the natural log of x is just the same as the derivative of the natural log of x, which is just 1 over x. So this shows us the power of knowing identities, that if you know some identities, you can often simplify the algebra that you need to do. And I want to talk a little bit about some trig identities now. So the 3 important ones is, 1 is cosine squared plus sine squared. And then we have the angle addition formulas. Cosine A plus B is cosine A cosine B minus sine A sine B. Sine A plus B is sine A cosine B plus cosine B sine A. So have we seen the first identity before? Does that look familiar to anyone?
From the unit circle.
Yeah, from the unit circle, it's Pythagoras. If I take a circle of radius 1, then my point on the circle is cosine A comma sine A. And so cosine squared plus sine squared is 1. So the first is just the Pythagorean formula. For the second one, for what we're going to do to find a formula for pi, we only need it in the special case when A equals B equals x halves. And this introduces another theme of mathematics, that frequently what you can do is you can calculate something in a special case and then deduce what's going on in other cases from it. So it turns out there's really only a small number of angles that we can directly compute. We can compute the sine and cosine of 0 and 90. Anybody know what other angles we can do? So what other angles can we calculate sines and cosines of? So we know there's the 3, 4, 5 right triangle, but we don't know what angle corresponds to them. So do you know any right triangles where you know what the angles are and you know what the sides are?
Is it like a 30, 60, 90?
The 30, 60, 90. And so let me see, I'm going to risk stopping the screen share and quickly going to the whiteboard. So if I give you an equilateral triangle like this, and I come down in the middle, if this is 1, this is 1/2, 1/2, this will be 30 degrees, 30 degrees, 60, 60. And so we get over here, this has to be √3/2. So we can do sines and cosines of 30 and 60 degrees because we know the equilateral triangle. There's one other triangle we know. What's the other right triangle we know? There's one other triangle where we know the sides and the angle.
Is it 45, 45, 90?
Yeah, 45, 45, 90. And so this is the isosceles right triangle. So again, as a rule of thumb, you look for special symmetries. And in this case, it's 1, 1, square root of 2. And so we know the sines and cosines of 30, 45, 60, and of course 0 and 90 as well. Everything else is really hard. But it turns out that by using the angle addition formulas, we can often reduce more challenging ones in terms of the ones we already know. And again, this is a very powerful theme of trying to calculate just something very basic and go from there. And so if we take A plus B equals x halves with A and B, if we take A and B to be x halves, then their sum is x. And when we substitute in for the angle addition formulas, we get a formula for cosine of x in terms of cosine and sine of x halves, and similarly a formula for sine of x in terms of sine and cosine of x halves. And so if we do a little bit of algebra, things simplify. And then what we can do is we can actually isolate. And we can eventually solve for the cosine and sine of x halves in terms of the cosine and the sine of x. So remember, we start off with the formula 1 equals cosine squared A plus sine squared A. We're trying to find a formula for the cosine of x halves, and we know the cosine of x is cosine of x halves squared minus the sine of x halves squared. So we need to take our initial formula, cosine squared A plus sine squared A, and take a value for A. Does anybody have a thought about what might be a good choice to take for A? So it should be related to x somehow. What would be a good choice for A? We're trying to find a formula for cosine of x halves. What might you want to try for A? So somebody give me a thought. What could we try? I need something related to x. I want to get cosine of x halves. What might be a good choice for a? Somebody needs to be brave and speak up.
I'm just thinking of kind of the unit circle. I'm not sure if that's
Okay.
kind of on the right track.
Well, we're on the unit circle. We have 1 equals cosine squared a plus sine squared a. We know cosine of x equals cosine x halves squared minus sine of x halves squared. I'm trying to get a formula for cosine of x halves. I need to choose a value for a. It's got to be something related to x. It's okay if your guess is wrong, but what would be a thing to try that's related to x? Now I'm trying to get cosine of x halves. I have a formula involving cosine squared a plus sine squared a. What should I try for a?
I don't have a number, but I'm just trying to find like number that would be easy to divide by 2, and we know on
Well,
the-
it's got to be related to x because we're trying to solve for the cosine of x halves. So you have to give me a as a function of x. You know, I could take a to be e to the x, but that seems ridiculous here. I need some relation between a and x. What's the simplest relation you could think of? You know, the simplest relation is I could take a equals x. That doesn't really help me. I want to get something involving cosine of x halves. So what might be a good choice for a?
It's just 2x. I'm just throwing something out, but you kind
So
of
good. So we could try 2x. That's actually going in the wrong way. So rather than multiplying x by 2, what could I do?
divided by 2.
Divided by 2. And the reason is we already know cosine of x is cosine x halves squared minus sine x halves squared. If I put into Pythagoras x over 2, I now have the following two equations on the bottom. I've got cosine x is cosine x halves squared minus sine x squared. X half squared, and I have 1 equals cosine x half squared plus sine x half squared. And so when I add them together, the sine parts cancel. And so I get cosine x is plus 1 equals 2 cosine x halves squared. So I can divide both sides by 2. And then I can take the square root, and I get the cosine of x halves is the square root of cosine x plus 1 over 2. And I can similarly get a formula for sine of x halves. So if I know cosine and sine at an angle x, I know their values at x over 2. And again, the more times you do this, the easier it gets. I'm trying to find a formula for x halves, so it seems reasonable. Let me go back to Pythagoras and let me put in x halves as my input. And so what this does is if I know 45 degrees, I now know 22.5. If I know 30 degrees, I now know 15. So we need to prove this formula. You know, cosine a plus b equals cosine a cosine b minus sine a sine b. In the interest of time, I'm not going to go through this in great detail. I'm going to just give you the high level sketch of where this comes from. I need to keep drawing right angles. So I'm going to assume a, b, and a plus b are all less than 90 degrees. And I'm going to just start dropping right angles. So I'm going to draw the line all the way down, giving my cosine a and sine a. I'm going to draw a line and give me a cosine b, a sine b from the other one. And now I'm going to draw another one straight down to the x-axis, and that gives me another right triangle with angle a plus b. And so if I want to find the sine of a plus b, I need to find the height of the vertical green line. If I want the cosine of a plus b, I need to find the length of the horizontal green line. And what I'm going to do is I'm going to break this green line or these green lines into lots of other things. And so we still need more right triangles. So the question is, how else can we get right triangles? What else can we do? Well, I can go from the blue line to the vertical green line. And so I'm drawing another horizontal green line, and that gives me yet another right triangle. And if you look at it now, I've got this nice rectangle, this green rectangle. And so if I want to find the sine of a plus b, it's going to be the green vertical line all the way up to the blue line of sine of b. And then it's going to be the green line continuing upward. If I want to find the cosine of a plus b, it's going to be the big one all the way up, on the horizontal, and then just subtract the base of the rectangle because I overshot. And so now I just start playing these games and I start looking at my triangles and try to figure out what the different hypotenuses are, what the different angles are. And so if we look at our red triangle, we've got that green line right where the sine of b hits. We know the hypotenuse is cosine of b. The angle is a. So the length of the horizontal adjacent side is going to just be the hypotenuse, cosine of b, times the cosine of the angle, which is a, which is cosine of a. So we know the long thing down there is just cosine a, cosine b. And then the rest is just using similar triangles and trying to figure out what the other lengths are. And so, we still have a right triangle, we have hypotenuses, we can figure out, again, using the trigonometry, what the bases and the heights are. It's a really good exercise for you to go through and try to do these calculations. But this is one way to see where these angle addition formulas come from, which is very carefully recording all these right triangles. Okay, how can we use this? Well, we can use this to get formulas for pi. And what I like about this is as close to calculus as you can come without getting calculus. Archimedes was almost there. He was doing everything geometrically. He didn't have the same notations that we have now. So one way to try to estimate the formula is, let's consider a circle of unit radius, radius 1. And what we can do is we can take a square and inscribe it inside the circle and circumscribe it outside. And then the area of the circle should be somewhere between those two. And then what we can do is we can keep bisecting the sides. And so if we bisect all the sides of the square, we get an octagon. And we can look at the inscribed and circumscribed octagons. And you can see, quite visually, that even by the time we get to the octagon, that's a pretty good approximation to the true area of the circle. It's getting very close very quickly. And so we can write down formulas exactly. So if I start off with a circle of unit radius, I've got my two radii emanating from the center of the square of length 1. The square is going to have side square root of 2. And so I can estimate the perimeter is going to be 4 times square root of 2, about 5.656. 2 pi is about 6.283. Okay, it's not terrible. And we can keep playing this game. If we now try to divide things in half with the 45 degrees, we're now going to have to calculate, what are the lengths of the sides of the octagon? We just calculated formulas for the sines and the cosines of the half angles. We know what 45 degrees is, so we can get 22.5. And so when we start to do that, the perimeter should be 8 times the length of one side. And so when you go through the calculation, using the cosine of x halves is the square root of cosine x plus 1 over 2. And similarly for sine, when the dust settles, we get the perimeter is 8 times the sine of 45 over 2, or 4 over the square root of 1 plus 1 over square root of 2, which is about 3.06. I'm sorry, so I'm giving you here half the perimeter. So it should be pi, not 2 pi. So I'm giving you half the perimeter. And so I've recorded here just doing, 8 sides, 16 sides, 32 sides, 64 sides. At 64 sides, we're getting 3.140. This is significantly better than what we've had at the start of the day. If you look at these formulas, do you notice any patterns? Do you see anything getting from one to the next? So what do you notice in common? What do you notice that's different going from one line to the next?
There's more square root symbols.
There's more square root symbols, okay. What about the square root symbols from the previous level? Are they still there?
It continues it and then adds another I guess,
Yeah.
like plus the root of 2 and then within itself.
Yeah, it looks like it takes what you had in the previous line and you add one more factor, which is 2 plus the square root of the previously largest. All the numerators seem to be 2. And what about the number that's outside the square root?
It's doubling.
It's doubling. Now, the only thing is, if you look at the very first line, that looks different than all the other lines. But notice, maybe there's a way to rewrite it because it has a 1 over root 2 in the denominator. So one of the biggest problems in math is you might actually have the correct formula, but it might be written in such a way that you don't understand, you don't recognize what you've got. I do a lot of stuff with Rubik's cubes, and at some point later in the semester, I will actually bring in some cubes and show you how some cubes that look very different from a standard 3x3 cube are actually the same if you just look at them the right way. And so I'm not going to go through and do all the algebra here, but if you actually do go through the algebra, you can show that you can rewrite the first one so that it does look like the others. And so when you do that, things look a little bit better. If you go up to 128 sides, we get 3.14128. So already at 128 sides, we're getting a pretty good answer. This is much better than what we had to do getting up to like 1 million before. Okay, so this is a good place to stop. And the goal for today was to just briefly introduce some results in sines, cosines, trig functions, talk to you a little bit about limits. Limits was the big idea in calculus. Talk to you a little bit about equations of lines. That's one of the big themes in Calc 1. And then we found formulas for pi. And the question is, why do we care so much about formulas for pi? Let's see, I should have, where's my first circle? Okay, here we go. So when you look at a circle, you can ask, what is the length of the arc you're going from, say, so many degrees? And it turns out if you have a unit circle, the perimeter of the circle is 2 pi, and the angular measurement is 2 pi. So that means that the length of the arc is the same as the length of the angle that it's coming from. That's not the same in degrees. In degrees, you have this annoying factor that you have to remember to include. And so what's going on here is the arc is essentially the same as the angular measurement in radians. And this is why the derivative of sine is cosine and the derivative of cosine is minus sine when we work in radians. If we don't work in radians, the derivative of sine is not cosine. You have a factor of 180 over pi. And that you have to be careful about. All right, if anybody has any questions, I can stick around for a few minutes. If not, feel free to email me. Remember, if you made comments today, to email me the comments you made, even if it was wrong. I want you to get in the habit of speaking and contributing. It is a hard thing to do, but the more times you do it, the easier it's going to be.